Hello everybody, welcome to Lab 4 Circuits by Isaiah Tannen. In this lab, the purpose is to understand how circuits and current interact with resistors, both in series and parallel, capacitors, voltage, and potential difference, and as well as how we can measure it with ammeters and voltmeters. We do this by predicting the outcomes of certain circuit setups and then measuring values to see if our predicted value is correct. Some fundamental concepts we need to understand is that overall closed circuits have a total change in potential equal to 0. We can understand this with Ohm's law. The total EMF minus the total current times the R equivalence will equal 0. And for R equivalence, we can see if they are in series, we just add them up. If they are in parallel, then it is equal to 1 over R. The system is a circuit, and we're using the PHET simulation. Circuit 1 had two resistors in series and two ammeters. The ammeter read 0.02 amps, which is in line with our prediction of 0.02204 amps, which we got by dividing the total EMF divided by the total resistance. Our voltmeter read -3 volts, and our potential differences from A to B, from the bottom of the battery to the top of the batteries, were 3 volts, and then from different points around added up to the 3 volts, giving our total loop a potential difference of 0. As we can see, these measures the potential difference throughout the circuit. From B to C, there is no difference, but from C to D it decreases, and E to F it decreases, totaling the increase from A to B. The resistances for the wire, we have 0. Ammeter, we also have 0. For the 47 ohm, we have 47, and for the 100 ohm, we have 100. Since the ammeter has no resistance, the I value remained constant when passing through. And lastly, the current flowed down just the path of the ammeter when we put the ammeter and the resistor in a parallel circuit, because it is the path of least resistance. And we can see that the new current is 0.0638 amps, which is read on both ammeters. For circuit 2, we used a 10 ohm light bulb and a 20 ohm light bulb. First of all, we see that when you connect it with the battery, the circuit will flow until the capacitor is charged, until the light bulb doesn't shine anymore, and we got this time as 15.64 seconds. And with no battery, where the capacitor runs the circuit and creates a flow, we get 15.74 seconds until it is fully discharged. For the 20 ohm resistance light bulb, the same exact thing happens, except with different times and different values. I used the ammeter to measure exactly when the current stopped flowing, but we got 27.94 to charge it and 27.61 seconds to discharge it. For circuit 3, we were attempting to find the time constant RC value. We used a 9-volt battery, a capacitor, a 30 ohm light bulb, and a 200 mF capacitor. This is my chart where we timed 1 second intervals to see how the voltage changed, or the potential difference changed, and we plotted that of ln of delta V divided by the initial V value, which was 9 volts. And we got this straight line where the slope is 1 divided by our RC value. So in order to get that, we got 5.98 seconds, and our theoretical value, if we take the resistance times the capacitance, we get 6 seconds. So our RC value experimentally matches up very well with our theoretical one. As for the what if scenarios, a real life ammeter versus an ideal ammeter, I used an ideal ammeter in the simulation. A real life would have some resistance, causing for a little bit of disparity in our current predictions and our measurements. Specifically also affecting the potential differences across it, there would be a non-zero value since there is some resistance and some current flowing through it. If there was no resistor in the circuit, the capacitor would instantly charge in theory. However, in real life, batteries have internal resistance, and therefore it would still take some time in a real simulation. However, in the PhET simulation, it would theoretically charge instantly.